So today we're going to be talking about confidence intervals for means. It will be a lot like what we did yesterday whenever we were talking about confidence intervals for proportions, just with a small twist. But some of the things will be the same and some things will be a little bit different whenever we start talking about means. All right, so just like for proportions, we're going to talk about, the things that are necessary in order for you to be able to set up a confidence interval. So there are a couple of conditions that have to be met. The first is that we actually need a simple random sample with no more than 10% of the population, right? So our rules of 10, or that is the only rule of 10 actually that applies for means. But it does need to be, a valid sampling technique with no more than 10% of the population. The population needs to be normal or are in the number of samples that we take, or the number of people that we choose to sample needs to be greater than or equal to 30. And sigma is known. What is sigma? The standard deviation of what? The population. That's right. So what this is saying is that the population standard deviation has to be known. Does that sound funny to anybody? Yeah. Why? If you already know the population standard deviation, what is the point in taking a sample, right? So if you really, in real statistics, you hardly ever know the population standard deviation. But if you know it, then this is going to work basically just like it would for a a proportion. Okay, so whenever we look at this and we start talking about a sample mean and then trying to come up with a confidence interval, here's kind of an example that we can use. It says a bottling machine is operating with a standard deviation of 0.12 ounces, so 12 hundredths of an ounce. Right, and that is the population standard deviation. That's sigma, because that is what it's operating with. That's not the standard deviation that we found in our sample. That is the actual standard deviation for the machine. Suppose that a simple random sample of 36 bottles the machine filled had an average of 16.1 ounces in each bottle. So the machine, we took 36 bottles that machine filled. We're going to use them as a sample, and we're going to say that they average 16.1 ounces in each bottle. And then we're going to come up with an interval with which we are 95% confident that the mean lies. Okay? So we're going to come up with a 95% confidence interval for where the mean would be. Yeah, and we're gonna develop a formula here for a one mean z interval. Do you remember yesterday we called what we did a one proportion z interval, and we did that because how many samples did we take? One. Yesterday we were dealing with a sample proportion, but today we're dealing with a sample mean. So this is a one mean. Why z? Where does the z come from? We get the z-score from how confident we want to be, right? So there's the z interval because we're talking about a confidence interval. So this is a one mean z interval, right? So what we'll take is, does anybody know the symbol for a sample mean? Mu, the Greek. All right, so this is the way you can remember it. Greek is for a population, okay? English alphabet characters are for samples, right? Yeah, it's X bar. X bar is the sample. Okay, so the sample mean plus or minus our margin of error. Yeah, which is so we use our z-score. Remember, our z-score comes from our level of confidence. Right? It's determined by our level of confidence times the what? The standard deviation, square root of n. Very good. So the population standard deviation over the square root of n. Okay? So whenever we're looking at this, what was our sample mean in this one?
16.1.
Okay, so this is 16.1 plus or minus. What z-score do we use if we want to be 95% confident? Okay, so 1.96 times sigma. So our population standard deviation is 0.12 over the square root of 36. So this will be 16.1 plus or minus. What's this going to be? Anybody run those numbers yet?
That's 0.02. 12 over 6, right?
Yeah. All right, then times the 1.96. 0.0392. Okay. And we can round this if you want to 2 decimal places or 3 decimal places. If your calculator is automatically rounding to 2 decimal places, hit mode. Hit mode. Okay. Hit mode. And then go down to where it says float, and then it says 0, 1, 2, 3, 4, 5. If yours is giving you 2 decimal places, it's on 2 right there. And what that's doing is that's telling your calculator to automatically round your answers to 2 decimal places. So if you go and put it on float, it'll give you as many decimal places as it can, or as you need, okay? So that's how you fix that problem. All right, so our interval here, if we subtract this, I'm just going to call this 0.04. Okay, and if we subtract that, what are we going to get? 15 point, no, yeah, 0.04. This will be 16.06. And then if we add it, so our interval is going to be from here to 16.14. Okay, so what can we say about this? Can somebody interpret it? Okay, good. We're 95% confident, because we use the 95% confidence interval, that the true population mean, what are we talking about though? That the true mean of ounces per bottle, right? That the true mean of ounces per bottle is somewhere in between 16.06 and 16.14. So you can kind of use that same thing. I am blank percent confident that the true blank, and you can either use a mean or a proportion depending on what you're talking about, and then use context. In this case, it's ounces per bottle, is somewhere in between, and then insert your interval, right? And just kind of roll through that same process. Tanzam? Uh-huh. The 100% confident? No. No. Yeah. No 100% confidence intervals. Is there any practicality to this where you know the population standard deviation? Not so much, which is why we're going to talk about this. Thanks for the segue, Christian. Yeah, so what if the conditions are not met, okay? So what if those conditions are not met? And the specific condition that I'm talking about is that sigma is unknown, okay? So what if n is less than or equal to 29 and sigma is unknown? Okay, either or. Then what we're going to do is we're going to change our distributions. We're actually going to use what is called a t-distribution instead of a z. Because remember, a z-score comes from a normal distribution, right? And so whenever we start talking about something where n is less than 30, do we expect our distribution of sample means to still be normal? No, because our n is too what? Small. If we make n really big, then the distribution of sample means should be normal. Therefore, whenever we're calculating, a 90, 95, 99% confidence interval, we can operate under the understanding of the normal model and know that, our population, or excuse me, our sample mean is going to be 95% of the time within 2 standard deviations of the population mean, right? But now, if we only have an n where n is less than or equal to 29, then now we're not so confident that the distribution of those sample means, if we took a bunch of samples, got their averages, and plotted them, we're not so confident that it would actually give us a normal distribution anymore, okay? Or the thing that's more likely to happen is this: sigma is unknown, okay? Which is almost always, whenever we're talking about real statistics, that you don't know sigma, okay? Circle this one right here. No matter what, if sigma is unknown, okay, this one right here, no matter what, if sigma is unknown, you automatically use a t-distribution. So here's the thing that's going to happen. It's going to be really rare, okay? It's going to be really rare that you end up using a z-distribution whenever we're talking about means. The only way that you get to use a z-distribution or a normal distribution in z-scores whenever we're talking about a mean is if the sample size is greater than 30 and your population standard deviation, sigma, is known. Those two things have to be true for you to be able to use a normal distribution. Otherwise, you're automatically going to use the t-distribution. Now, the t-distribution is going to look a little bit different than the the z-distribution, and we'll talk about it and how it kind of shifts and changes, because it's kind of a new idea whenever we start talking about the t-distribution here. So a t-distribution is what we're going to use when the population standard deviation is unknown. So when finding a confidence interval for a sample mean, what we'll use is a t-score, okay? So we're going to use a t-score rather than a z-score, because the z-scores go with a normal distribution, the t-scores go with a t-distribution. All right, so you can see what I've got up here, okay? The z-distribution is this black line, okay? While the t-distribution is the green line. So you notice that the z-distribution is kind of higher in the middle, right? And the z, you could also call it a normal distribution, right? It's higher in the middle. And then for the t-distribution, it's a lot flatter, okay? Which one? No, it's supposed to be pretty even, okay? You want it to be symmetrical, even though it's a t. And the t-distribution does kind of start off lopsided, but as you move, as you get more and more degrees of freedom, that's another idea we'll talk about in just a second. But as you move, then what ends up happening is it does get more and more symmetrical. The t-distribution does as you go along. Yeah, not that big of a deal. Okay, so if the z-distribution, let's see if I can kind of illustrate this for you. If we move one standard deviation to the left and to the right, we expect the z-distribution to contain how much data in there? Do you think a t-distribution has 68% of the data within one standard deviation? No. Why not? Yeah, because when we look at these, the z-distribution, all of this space right here, all of these different data points that are included in the z-distribution right there are not included in the t-distribution. So the amount of data that lies within one standard deviation of the mean, whenever we're talking about a t-distribution, is less than what's one standard deviation away from the mean in a z-distribution, right? So what's going to happen is, if we want to be confident, say we wanted to be 95% confident with a z interval, okay, if we wanted to be 95% confident with a z interval, then we know we need to move how many standard deviations? 95% confident? 1.96, right, is what we're looking for. So what we're saying is, if we move by 1.96 in either direction, we make our lines here, then what's contained in between there for that z-distribution is going to be 95% of the data points. That's going to be there. But with a t-distribution, if we move that same distance out, Do you think we're still going to contain 95% of the data? No, because if you notice, the t has a lot more space out here, right? Whereas the normal distribution starts to get really small as you move out a little bit. The t doesn't flatten out so quick, okay? So it's got more data points out here away, right, than the z distribution does. So if we wanted to be 95% confidence with a t interval, do you think that our range is going to have to be, our interval is going to have to be bigger or smaller? It's going to have to be bigger, right? So that's the whole idea behind going to a t-score. Since we don't know the standard deviation, right, the standard deviation could change a lot from r, because what we're going to use when we use a t-score is we're not going to be able to use a population standard deviation. So where do you think we're going to get our standard deviation from? That's right, we're going to get it from the sample. So now that we're using a sample standard deviation and a sample mean, there's a lot more variation in what we're talking about than where we're using a sample standard or a sample mean and a population standard deviation. Does that make sense? So since there's more uncertainty in how good not only our mean is, but also in how good our standard deviation is, now we better do what? If we want to be 95% confident, we better reach out a little bit further to try to make sure that we encompass everything that we need to in that 95% confidence interval. Does that make sense? So we're kind of stretching the confidence interval because of all the stuff that we don't know. We don't know the real mean. We don't know the real standard deviation. So if we want to be that confident, we got to go a little further. Okay? So a t-distribution is 4 means. And in the calculator, just like there is, a normal CDF, a normal PDF, an inverse normal, and just like there is a Z interval, there's also everything for a T. So there's a T PDF, a T CDF, an inverse T, and a T interval, just like the one for normal. Okay, so we'll have all of the same operations in the calculator, and it'll be under distributions because the T is a type of distribution. Okay, so T is a type of distribution. But here's the important thing. T is dependent upon what we call degrees of freedom. Okay, so T interval and the T distribution will actually change. The normal distribution never changes. But a T distribution will change with degrees of freedom. And degrees of freedom are just n minus 1. Okay, so whatever your sample size is, minus 1. Okay, so here's a way to think about degrees of freedom. And this is why degrees of freedom is n minus 1. Because when we say freedom, we really mean, freedom. You're free to do whatever you want, right? So I'm going to give Patrick these markers. Okay, I've got 1, 2, 3, 4, 5, 6 markers. Okay, they're all different colors. We got a green one, a yellow, a pink, an orange, a blue, and a purple. And I'm going to give all of these to you, Patrick. Go ahead and take those. Okay, and Patrick, I want you to choose freely which one of those markers you would like. All right, now pass them back to Armand. So Patrick took the orange. Armand, choose which marker you would like. Armand takes the pink, naturally. Okay, Connor, the blue. All right, Marika, you take the yellow. Tanzam, you take the green. Now go to CC. CC, do you have any freedom? No. Who was the last person to have any freedom? Tanzam. So with 6 markers, how many degrees of freedom were there? 5, because the first 5 people actually have a choice to make. That 6th person can only take whatever marker is handed to them. And when we're talking about means and stuff in statistics, it makes sense as far as degrees of freedom go. Okay? So here's what I'm going to do. I'm going to give you guys 5 degrees of freedom. We're going to come up with an average right here, and I'm going to give this class 5 degrees of freedom. I'm going to take 6 numbers. You get 5 degrees of freedom, and I want you to try to mess me up. I'm going to make the numbers that you give me average 1. Okay? You have to give me integers. Okay, you have to give me integers, but I'm going to make them average 1. You got 5 degrees of freedom. The only one you don't get freedom on is the last one. Okay, so Shelby, pick a number. 937. All right. Christian, go ahead. 938. Caleb. That's not an integer. I didn't want to have to deal with a bunch of decimals. It could still work, but I just didn't want to have to deal with a bunch of decimals. 500. Marshall? 4,000. I'm going to make them average 1. 1, 2, 3, 4. All right, I need one more. Who wants to give me this last one? Huh? A Googleplex. I don't have enough room on this board to write a Googleplex. Do you want it? Did you say 6 million? Negative 6 million. Okay, so let me get rid of my minus or my plus sign right here, and I'm going to put minus 6. 1, 2, 3. 1, 2, 3. Okay, that's 1, 2, 3, 4, 5. Your 5 degrees of freedom are over, but we're going to use how many numbers? 6. The thing is, this last number is not free. Okay, those first 5 numbers could have been whatever you want them to be, but the last number is not free. If this thing is going to average 1, let me not call it n. I'll call it x. Okay, if this thing's going to average 1, I'm going to multiply by 6 on both sides. So 6 should equal all of these numbers. So go ahead and add those together. I got rid of the 6 already. 937 plus 938 plus 500 plus 4,000 minus 6 million. And what do you get? Negative 5 million. 993,625. Plus X. So I'm going to add this 5,993,000 plus, or sorry, 625 to both sides. So that plus 6 makes 5. 631. That'll make it happen, right? I can get whatever average I want to. You're free on all of them except for the last one. You guys could make those numbers anything you wanted to. The only problem was you had with a sample size of 6, you had 5 degrees of freedom. That last one is locked in on what it has to be in order for you to be able to achieve the number that you want. Does that make sense? So degrees of freedom is n minus 1. Does that make sense why they're called degrees of freedom? Yes, n is the sample size, right. So if we had a sample size of 35, how many degrees of freedom would there be? 34. Yeah, that's it. Okay, so here's something else that you kind of need to see. Here is this is a normal distribution in the top left. So what we're dealing with here is a normal distribution. And each one of these graphs have a normal distribution. Okay, so you can see this is a normal distribution, but then the one underneath it right here, the bottom line in this second picture right here, this bottom line, okay, the one on the bottom right there is the t distribution with 3 degrees of freedom. The one down here on the bottom left is the t distribution with 7 degrees of freedom. How does it compare to the normal distribution? It's getting pretty close, yeah. And then what about the t distribution down here with 20 degrees of freedom? Yeah, it pretty much gone back to being the same, right? So this is what I want you to do real quick. Take your calculator, all right? And in your calculator, I want you to go into second distribution. I want you to go to normal CDF. Okay, and I want you to go from 1, so just go from 1, and we'll just use 1 to 99. So go from 1 to 99 in a normal CDF and hit enter. What do you get? All right, so 0.1586. So that proportion of your data points are from 1 standard deviation to 99 standard deviations above the mean, right? So now go in and hit second distribution and go down to a TCDF. It's almost at the bottom, right? Now I want you to go from 1 to 99, comma, because the T distribution, remember, what does it depend on? Degrees of freedom. So you have to put in 1 comma 99, and then you have to tell it how many degrees of freedom. So first, I just want you to put in 2. So put in 2 degrees of freedom and hit enter and tell me what you see there. Okay, so with only 2 degrees of freedom, there's a lot more data, more than 1 standard deviation away, right? You could get a lot more data out there if you only had 2 degrees of freedom. That would mean your sample size was what? If you have 2 degrees of freedom, how big was your sample size? 3. That's exactly right. Okay? So now go back and do TCDF again, but this time change the degrees of freedom to 30. Now, how does that compare to the normal distribution? They're getting a lot closer, right? Okay, so that's why some people will say that if you have an N value that is greater than or equal to 30, some people will say just go ahead and use the normal distribution all the time because that gives you 29 degrees of freedom. The T distribution and the normal distribution start to get really, really close. I was literally looking at 2 different books yesterday. One of them was saying if N is greater than 30, just use the Z-score, right? The other one was saying if you don't know sigma, always use the T distribution no matter what. It was like, okay, which one do you do? Well, the reality of the situation is that either way, it's going to end up being pretty close, okay? So we're just always going to stick to the T distribution if we don't know sigma. It'll kind of simplify things for us, and we can just keep going with that, okay? All right, so here's our exact same question. The only difference is now, so now what we're going to do is we're not going to know the population standard deviation. So this is the same problem before. So if you just want to look at the same example we had before, we're just going to change one little thing on it. Say that again. Yes, it's for the sample. So this is what we're saying. A bottling machine is filling bottles. Suppose that a simple random sample of 36 bottles the machine filled had an average of 16.1 ounces in each bottle and a standard deviation. So this is the standard deviation, once again, from the simple random sample. So our sample mean is 16.1. That's the average here. Our sample standard deviation, that's S, is 1.2. I want to give an interval with which we are 95% confident that the mean lies. Okay? So if we look at this one right here, then what we're going to have is S divided by the square root of N. It was too big. The screen ended up being too large for it. It didn't work out. I'm going to, actually, can I keep that screwdriver for a little while? No, you got to have it?
Adjust it up underneath there? Oh, what?
Okay, so what we're going to do is we're going to take our standard error here that we're looking for is going to be our, since we don't have sigma, instead we're just going to use S over N to come up with the standard error for this set, right? So whenever we're dealing with this, it's going to work just the same. We're going to have X bar plus or minus, but now where before we had a Z-score, this time we're going to have a what? A T, yeah. And like the Z-score depended on how confident we wanted to be, right? The T-score is going to be a combination of confidence and what else? Because T-score doesn't just depend on how confident we want to be. It also depends on degrees of freedom. Yeah. So whenever we're figuring out what our z-score is, if we want to be 95% confident, we just use a z-score of 1.96 every single time, no questions asked. But if we want to be 95% confidence with a t-distribution, it depends on our degrees of freedom. Okay? So it depends on our degrees of freedom times the standard error, which will be s over the square root of n. So you can see these formulas for a population mean are slightly different than the ones for a proportion, right? So we're coming up with a confidence interval for proportions. S is the sample standard deviation. That's right. Yes. All right. Now look at what this one is called. This is the formula for a one mean because we took one sample and we found an average or a mean, but it's a one mean t interval. It's not a one mean z interval, right? It's a one mean t interval. Why is this one a t instead of a z? Because we have to use the t distribution instead of the normal distribution, right? So they just changed the name on it. Real simple name change, though. It makes sense. Okay? So in your calculator, you can go in and you can hit you can hit stat, go over to test, and there's a t-test, but we want a t-interval. Yeah, t-interval. All right, we're giving it stats. So what I'm going to do is I'm going to go in and ask for the mean. That is 16.1. The sample standard deviation was 1.2. What are my degrees of freedom in this one? Yeah, we took a simple random sample of how many bottles? 36. Therefore, so our degrees of freedom, n is going to be 36. It'll calculate the degrees of freedom for you. And then our confidence interval here is going to be 95% confident. And then you can hit calculate. And it gives it to you. What do we get? Yeah, 15.964 to 16.506. Okay? Now, I actually want to do this because I want to talk about what's happening here. This is 16.1, right? Yeah, 16.1 plus or minus t. So what we want to do is we want to calculate a t-score, right? If we want to be 95% confident, okay? So here's I'm going to call this a t distribution. I'm going to draw it flatter. Yeah, I can use an inverse t. But remember, if we want to be 95% confident, okay, then what percentage of the data lies out here? 2.5%. And then 2.5% lies out here. So if I use inverse t, okay, so let me go into second distribution. I'm going to go down to inverse t. And I'm looking for 0.975% of the data to be to the left. But if I'm using a t distribution, once again, it always needs to know the what? Degrees of freedom. How many degrees of freedom do we have? 35. And you can see it comes up with a t-score of 2.03. Okay. And then we have S. S is 1.2. 1.2 divided by the square root of n. What was n? 36. Okay, so we get 16.1 plus or minus 0.406. And if we subtract it, we get 15.694. What do we have up here? 15.694. All right, and then all the way to, if we add it, we're going to get 16.506. Right? So you can come up with it either way. But I wanted to talk about how to get the T's, right? The T's aren't that difficult. We just have to know when to use them. When do you use a t-score? If you don't know the population standard deviation, or if If n is less than 30, then you just automatically go to a t-distribution, okay? And then it works out the exact same way. So you can see this one right here, and we would explain the 95% confidence interval the exact same way. So that is how you can find confidence intervals for means.